Good afternoon, everyone. Good afternoon, Christine. Thank you very much, Christine, for being with us again. I think today is lecture number 4.
Yes.
Yeah. So, Christine, I don't need to introduce you anymore. People know you, so you're welcome to start with your presentation and to recommend people to fill out the poll.
Thank you so much, Prof. Yeah, so the poll, I'll leave it open. I've frozen time. I have the magical powers to freeze time a little bit, so I'll leave it for a few more seconds. We'll do another poll just now about the presentation I'm going to do, so the new work specifically on hypothesis testing. So if you can get logged in and everything, then we know you're set for that poll as well. So we'll start today's class again just by recapping or just finding out if there's any questions about the previous lesson, and then we'll jump into hypothesis testing. So I'm going to start time again, and there's about 9 more seconds left to tell us what languages you speak. At the moment we have a lot of European languages in here. And if you missed the poll, you can tell us in the chat, but just log in so that you're ready for the next one. So I see there's a 4th response, but I don't see it showing up here. That's interesting. Okay, so let's see where we are. So this works. Okay, so any questions? So if anyone wants to switch on their mic or in the chats, tell us any questions about what we did on Monday, yesterday. If there's anything about distributions that you're unsure about or just want some more clarity about, let me know before we move on. And of course, the hypothesis testing is based on distributions. So we're moving into hypothesis testing today. And a lot of hypothesis tests are built on distributions and distributional assumptions. So it's quite important, the theory, although we didn't go into the theory. I think most of you have done something with distributions. But yeah, we'll look at a few assumptions today as well. Okay, so no questions it seems. So then on to the homework. So I'm gonna just skip over to R. So I left you with this problem yesterday and said, firstly, there was this code that I wanted to know if anyone could fix it. So if anyone found a solution how to fix this code so it actually gives us the right answer, please let us know. But the actual problem that I want to look at now is to see if anyone could figure out how to calculate the row and column averages, and I added in their totals as well. So I did upload this file on Moodle. So just for that, let's just call this Matt. I'm just going to assign this in there. So I'm just going to make sure that everyone can get the same solutions. I'm just going to run my seed value again. You have to rerun it. If you've done something else, you might have to rerun it again to get the same results as me. And then I'm going to just generate this matrix with random values that were from a t distribution with, that's because we're using the RT function, with 13 degrees of freedom. We calculated a bunch of values and we said, put this in 15 rows, 5 columns. So if we view this, let's just see what happens if we say view maths. There it opens it, and you can see we have the variables, or it automatically assumes that it's variables in the columns and observations in the rows. So we have all of this data. And then my challenge to you was, how would we, for instance, calculate the row and the column averages? So let's say we want the average of each of these rows. So I want the average for row 1, average of row 2, and so on. Could anyone figure out what function, if there's a built-in function to do this? So I specifically said without making use of loops. So we can do it with loops. We don't want to do it with loops. So any ideas?
Christina, there was a raised hand by Mpumelelo earlier, but the hand was lowered again. So I'm not sure if it was active. Maybe Mpumelelo, if you wanted to make a comment or ask a question, please don't be shy.
Thank you. I wanted to ask a question about hypothesis testing.
Yeah.
That usually use it for inference purposes, but then could we sort of like extend it for establishing causality?
Well, I think that's a tricky question. I guess you, like, some people would do that. I would be very careful about doing that. Just thinking specifically about where your data comes from. So if you get your data in an observational study, so you just go out into the field and you collect data, then that's not really a good data set to use for causality. You would have to design your experiment to control your different factors if you wanted to make any inferences about causality. So I wouldn't do it on an observational study, and most of our data sets tend to be that, unless you are working with experiments specifically, then maybe you could go into that field. That's not something I've worked with before, really. I've worked more on the inference side. But I'm sure if you collect your data in an appropriate way, then there should be a way to do that. Don't know if that answers your question.
Thank you.
Okay. Okay, any other questions or comments or any ideas yet? What function I can use to calculate row averages? Let's see who. I might pick someone here at random who I haven't spoken to before. Let's see. Mabato, any ideas? Or Wynand? Any suggestions? Okay, I see you've put something there. Yes, so you found that one. So you called yours TR matrix, and I see you used an equal sign in to do the assignment, which does work. Sometimes you will run into issues with that though. So that's why I normally use this arrow type thing, because I know I'm not going to run into issues with that. Sometimes doing just an equal could cause issues in some packages, but it's not a very common issue. Just be aware of it. So you then said if you want to calculate the sum of the rows, you would use the row sums function. So if we use row sums on that matrix, I'm just going to run that. You can see we end up with 15 values here. So those are the 15 sums of the rows. So you then suggest that we could go and divide this if we wanted to. We could divide that by saying length of the original data set. So just looking at row sum, so length of, let's do that. So, well, let me actually follow your code a little bit more closely. So I'm just going to call this RS, so I don't have to type all of that each time. So I'm going to do that, and then RA for row average, and that you've said is row RS divided by length of RS. Okay, so if I run that, I end up, oh, and this is a trick I wanted to show you. I forgot to show it the other day. If we put all of this in brackets, if I want to print my results and do the assignment, I just put brackets around the entire row, and then it will output that for me immediately. So just want to double check always with the length function. Sometimes you run into issues with that. So if we do length of this, it's going to give us 15. So that's correct. So it's a good idea to just always check what's happening. Now, there is another way to do this. So I see you've done something similar for the columns. Is there another way to get the row averages, for instance? I'm just going to put this in brackets so we can see it again. I'm going to start typing row, and then we can see what comes up. And you can see there's a few functions that start with row, and one of them is row means. So if we use row means on that, oh, that predicted something else. I should not have pressed enter at that moment. Let me just delete that. There we go. Then you can see we actually end up with exactly the same results as you got with your function. I know it's not exactly the same. That's interesting. So one of our functions is not working this out correctly. So let's just see if we look at the first ones. I'm getting 0.1549241. So I think let's try something else. Let's see which answer is correct. So I'm just going to do one manual calculation. I'm going to say, give me the first row or the first few rows of that. It was probably not the best idea to call it mat because it keeps predicting other things then. Let's just do that. And then I'm going to just say sum. And let's try, we copy and paste these values. Just see what we end up with. So, oh, I think I know what the problem is. So if you look at this function, I'll show you now. We want to divide this by 5. So if I divide by 5, I get the answer, the 0.15 as my answer, which is what I got with the row means. So what you've done here is you calculated the sums of each of the rows, and then you divide it by length of RS. And when I ran length of RS, we saw that that is 15. So it went and calculated how many rows there are. While when we want to calculate this, you want to add these 5 values and divide by 5. Add those values, divide by 5. So you were dividing by the number of rows instead of the number of columns, which is how we would calculate the average for the row. Does that make sense?
Yes, Prof.
Okay, cool. So yeah, so close, but this length function was just a bit of an issue. So that's why it's so important whenever you do calculations, always go check your code, run it, see what your output at each point is, double check maybe 1 or 2 values just to make sure everything is actually doing what it's supposed to. And then you, when you know that the calculations make sense, then it's fine. So we can try something else. I just want to show you this length function can sometimes cause some issues as well. So let's just see if it does what I think it might. So if we say length of mat, let me just click there before I press enter. So this length, it went and said, okay, we have 75 elements. Something else you could have tried is the n column function. So there's 2 of them, and I often forget which one to use. So I'll try both of them and see which one gives me the correct answer. So this,
I think that one's a column.
Yeah. So there's actually, depending on what data structure you work with, whether you use the lowercase or the uppercase one, it can actually make a difference to what it gives you. So in this case, it works. So with matrices, it works. I know with data frames, you might run into issues. So in this case, if we change the length to ncol, I normally use the capital letter one because it always works with the data frames. So if we run that, we should change this then to mat, not RS. Okay, and then we get the right answer. So you were on the right track with it. Well done. It was just that one little issue that was a problem. Yeah, perfect. Cool. So yeah, so you can see there's some built-in functions for totals you'll see that you have the row sums function or the col sums function. So yeah, there's some nice built-in functions that you can use rather than going the loop way. It's just a lot less coding. Just have to make sure you're summing and averaging the right stuff. So that's pretty much it for this homework. I'm not going to finish the rest of this off. I think everyone will be able to do that. So let's get back to today's lecture then. So hypothesis testing, I'm not going to go into like heavy theory or explain everything from scratch. I saw yesterday most of you have the basic ideas. So I just want to give you a kind of an overview of a few things. Isaac, yes, I see your hand up.
Hello, Chris. I would like you to explain something for me, like, and at what condition? Let's say, for instance, we are looking at the binomial distribution. We want to find the probabilities, and at what condition will you have to use the P binom, and then and at what condition will you have to use the D binom? Well,
Okay.
I would like to light on that.
That is a very good question. I actually am not 100% sure. Let's go to the help file and see. I've never actually used the D binom function. So let's see what the help says about these functions. So let's see if it works now. That trick that I told you about. Yes, it worked this time. Okay, so D binom, if we just look here, gives a density, and this so I'm not 100% sure, to be honest, what is meant by that. So the D binom function takes in what arguments? It takes a vector of quantiles. So what I'm going to guess is happening with that D binom is it probably, if you give it a vector of values, maybe it fits a binomial curve to it. That's going to be my guess. I haven't used it before, so I'll definitely, let me write that down. I'm going to go see if I can get you an answer by Friday, and see if I can figure out what the difference between those two functions are, and then I'll let you know Friday at the beginning of the lecture. Okay, cool. I see Mpumelelo has the answer for us, gives us the density. Yes, that makes sense. That it would give the PDF instead of the CDF.
Okay, so hello, Chris. Yeah, so can we say now? Okay, what with respect to the D binom, it looks like the probability of observing a certain variable. Can we conclude on that? Maybe we have a list of things and we say, okay, what is the probability of observing 2 from the data that we have observed? Can we say that is the condition under which we can use the D binom?
Okay, so it sounds like if this is for the PDF and not the CDF, then it means that if I want to calculate the probability that X takes on a specific value, not a range of values, we can use that. So we can actually test that very quickly. If we go back to, let me just do that. We go back here. Let's say we want to calculate the probability of X taking on a specific value. So I'm just going to add it here in the code, and we can see if it works. So if I wanted to calculate the probability that X is equal to, let's make it 7, then I could, let's see what happens if we use that function. So if we say D binom, and we take 7 and 20 and 0.34. Let's see what that gives us. And then just to check whether that is actually for the PDF, I'm going to do the calculation in another way. So I'm going to use the P binom function. And then I'm going to say, let's say 7, 20, and 0.34. So I'm going to say, let's take the probability that X is less or equal to that minus the probability that x is less or equal to 6, which only leaves 7 then for us. So if we run that and we get the same answer, yes, we get the same answer. Thank you, Mpumelelo. You have solved the problem for us. So if you want to calculate the probability that x takes on a specific value, then you would use the d binom function. So I've always just used p binom this way. I never thought about doing it in another way. So now we know. Isaac, does that solve the problem for you?
Yes, please. Yes, please. Thanks.
Okay, perfect. And thank you, Mpumelelo. Okay, cool. So any other questions before we move on with the hypothesis testing? Doesn't look like it. Okay, cool. So I've just done some, yes.
Can you, I just want to see what happens if you try to replace 7 with a vector, or maybe 2 numbers.
A vector. Okay,
Yes.
let's try that. Let's see what happens if we do that. So let's see, let's put in the d binom. Let's put, I'm going to guess that we do it this way. I'm going to concatenate 6 and 7. So again, this is something I've never done before, so we'll see if it gives us errors or not. Let's try that. Okay, so it gives us 2 probabilities then. So it looks like it calculates those 2 probabilities separately, and then it gives us a vector associated with each of the quantiles that we put in.
Yeah, so
it
makes sense.
And I'm guessing if you wanted to calculate the probability that x is 6 or 7, then you would just say sum of these, and then that should just give you that total probability. Yeah, so then it just adds it up for you.
Nah, super.
Cool, awesome. So we can get lost in playing with these functions, see what they do. Okay, cool. So then back to the hypothesis testing. So why we do hypothesis testing is basically to see whether our theories make sense. So if we have sample data, we can test the theory using that sample data. Now, null hypothesis is what we assume is true unless we prove otherwise. So we're trying to always, with hypothesis tests, disproves the null. So our theory normally goes into the alternative hypothesis, and I've just given some extra notation there. So different textbooks use different notations. Some use an A, some lowercase, some uppercase, some use a 1. The null is always written the same way. So then the steps involved in hypothesis testing, I don't know how recently anyone did this, but the basic idea is you want to set up your null and alternative. You want to determine a rejection criteria, and that rejection criteria can be with a p-value, and I think that's what most people tend to do, especially if you're not a statistician. You run your code, and the machine spits out a p-value, and you use that to make your decision. I was actually chatting with someone the other day who said the only thing she remembers is that if your p-value is less than 0.05, you're happy. That was basically what she remembers from her stats class. But yeah, rejection criteria, you can also use distributions and set up a critical value and then compare your test statistic to that. But most of the time people calculate a test statistic based then obviously on the sample data and the theory that they have, and they use that to calculate the p-value. Software luckily does p-values for you, and there's many ways to do p-values. So you can do it based on a distribution, or you can do calculate your p-values based on simulation studies, on bootstrapping. There's a few different ways of doing it. It depends on your context what you would be doing. And yeah, that's basically it. Then you would make a decision. So you would say, I reject the null or I don't reject the null. And your conclusion is always then in terms of your problem. So I always tell my students, your conclusion should be in such simple language that anyone who has never done statistics, your 7-year-old brother or sister, should be able to understand what you are saying. They might not understand every single word in the sentence, but the concept should come through. So that's what we tell our first years all the time. So if we look at hypothesis tests, I've picked 3 of them for us to do today. So 2 t-tests and a test for independence, just to show you how you can approach these in R. So basically, the one sample t-test is a very, very commonly used test. It normally tests theories about the mean, and you have your sample data. We use this when we don't know population standard deviation. So there is a test we can do when you know the population standard deviation, which often in real life is not the case. So that's why we go to the t-test and why it's so commonly used. So some assumptions just to take note of is, and this is especially important, that's why I said for small samples, your data should be approximately normally distributed. So I won't go into the theory of that, why it's important. The short of it is just central limit theorem. If you've heard those words before, you might remember them. But basically, if you have small samples, you want your data to be approximately normally distributed. Otherwise, you're doing a test, you're going to get a result. It's not a good result, though. So, or it might not be a result you want to rely on. So I did some reading. Some textbooks say if your sample is less than 30, then you want it less to be approximately normally distributed, the data. Some say less than 50. So that cutoff point varies from textbook to textbook, and so don't stress too much about that. The idea is just that you should be careful. The smaller your sample is, the more careful you need to be with these assumptions. Then the other important thing is your sample needs to be a random sample, which just means that your elements don't influence each other. They're independently selected of each other. They might not be influencing each other. So that is very important in a lot of tests. So if your assumptions are violated, there are other tests you can do. We won't go into that too much today. It's not a heavy theoretical lecture, thus. So basically then for a t-test, you are going to have your null, which is that the mean is equal to some predefined value, which I just called mu naught. And your alternative is then the theory that you're investigating is either that your mean is actually less than that value, that it's not equal to that value, or that it's greater than that value. So what your research question is will determine which one of these will be appropriate. Then your rejection region, if you wanted to create or go and find an actual rejection region, you would use your t-distribution with n-1 degrees of freedom. So n is just your sample size. And if you don't want to do that, you could always go the p-value route as well and calculate a p-value, but you would use that same distribution to calculate your p-value. Then your test statistic, very, very simple, is actually just sample mean minus your theoretical mean that you're interested in, divided by the sample standard deviation over the square root of n. So in simple terms, if we look at this formula, what it's basically telling us is we want to see how many standard deviation units or standard error units away from this theoretical mean we find our sample mean. So, but the good news is you don't actually need to use this formula. You can go type it in manually in R, but R does all of these calculations. So all of this is happening in the background. And then all you need to do is figure out what decision and conclusion to make. And it's good practice to just always mention your significance levels so people know how confident they can be in your results. And then obviously in plain words, tell them what the conclusion is. So I have a few examples for us that we're going to work through together. And the first one is back to our possum data set. So you'll recognize this from the help files. The possums that we are looking at in R, in that open intro package, specifically in the possum data set, the data is from this source, and you can see they were looking at mountain brush-tailed possums. So I went and I just Googled how long is a possum's tail, and I ended up finding a document. I've added the link here. It's a wildlife survey, document from the wildlife people in Victoria in Australia. So you can go and click on that. I added the link there so you can see where I took my screenshots from. But that is basically what a common brush-tailed possum looks like. So you can see not quite the same as what we have the data for, but they'd say there that it's these common brush-tailed possums have tail lengths of 25 to 40 centimeters. Obviously, we can't go plug all those values into our hypothesis test. So I decided I'm just going to take the average of those, and that's going to be my average tail length. So we're going to assume that the average tail length of a common brush-tailed possum is 32.5 centimeters. So suppose we want to go and test whether the average tail length of common brush-tail and mountain brush-tail possums differ. Now, our first thing that we need to do is we need to go set up our null and alternative hypotheses. And that's where I have a question for you guys. I want you to do that now. I have a few options here on the screen and a very cute picture of a possum. I want you to identify the correct null and alternative hypotheses. So I've put the question up there, and I'm giving you a minute to select one of these options. And I'm not displaying the results this time until everyone is done. Then we'll see what the correct answer is and what everyone chose. Just under 30 seconds left. So if you want to check or test whether the possums have different tail lengths, how would you phrase your null and alternative? So I don't see any answers yet, so time is going to stand still a little bit until we have some answers. Is one coming in now? Need a few more. So I see there's 23 students in here. So I want a few more than one answering. See, we have another one. Oh, and sorry, I just realized that I made a bit of a boo-boo here on my slide. Don't know if anyone noticed this, but that should be an A each time. So that's my alternative. So I don't know if that's what's throwing people off, but let's just fix that. This is why we don't copy and paste everything, except that we do. There we go. So the second one each time is my alternative. I see someone undid their answer. There's some more coming in now. I'm going to start the timer again, and then you have 5 seconds left to answer. Okay, there we go. So let's see what you said. So most of you chose the correct answer. The correct answer is that one. So why is it the correct answer? Because my alternative always has my theory. I want to see if the tail lengths differ. And another thing that I didn't mention earlier is just when you set up a null and alternative, your null can never have an or your alternative can never have an equal sign in it. It's always an inequality. So either greater than, less than, or not equal to. You can never have an equal sign. So you can't have a greater or equal or a less or equal or a equal in your alternative. So this was the correct answer. So that's what we are going to test now. So we go back to R. Let's do that. So on Moodle, you will see that I have added a file for you for today's session. So first thing we need to do is we need to load our Open Intro library. Otherwise, we're not going to find our data. So then if we think back to those assumptions that we make, we said that if it's a small sample, especially, we want to make sure that our data is at least approximately normally distributed. So first thing we want to do maybe is just basic descriptors, do a histogram. Luckily, we don't have to think too much with this one. Open Intro, oh, not Open Intro, R will do most of the work for us. So we have possum here, and we are interested in the tail lengths. So if I do that histogram and I look at that, you can see it's not 100% normal. I would not call that normal myself, but it's close enough. You can see there's some symmetry. Now, if we also then just maybe do a summary of this, let's just get a summary of the possum tail lengths. That's it. Then it hasn't shown us how many observations we have, but we can see here our mean and our median are very close together. And that's bodes quite well for us. It confirms that it's not 100% symmetric, it's not 100% normal, but at least it's close enough to make us happy. Now, if we also look at the data set, we'll see that if I use the summary function again, this should work. If I just say summary of possum, then we can cheat the system a little bit, and we can see, oh, if we add those two values together, we'll get 104. So we can see there's 104 values. So it's not a particularly small sample. So just because it's not 100% normal doesn't mean we can't do a t-test. In this case, I'd be comfortable doing a t-test here. So now we need to do the actual t-test. So any guesses what function we need to use? Well, I'm going to just start typing t-test and see what happens. Oh, and there's, what would you know? There's a t-test function. So we can go and read a little bit about it. R is very good for people who are lazy, no one to remember things. You can just guess half the functions. So you can see here, this function tells us you can perform 1 and 2 sample t-tests on vectors of data. So it tells us here that we have X, we have Y, you can put your alternative, you can specify your null mean. So if you go check there, it says mu is the number indicating the true value of the mean or difference of means if you're doing a 2 sample test. You can indicate whether you're working with paired data, whether the variances are equal or not. Your confidence level can be indicated here as well. And there's a formula bit, which I've never really used, but I'm sure it has some uses there. You can subset things as well. And then right here at the bottom, you will find that there are examples as well of this function being used. So there's some extra information that you can also go read here that could prove to be useful. So if we want to do a t-test here, we're starting off with a very simple one. So it is going to be t.test. And we are going to first enter then our data. In this case, our data is possum. And we are specifically looking at tail lengths. Now, if I run this, by default, it's going to do a 2-sided test. So you can see R tells us immediately, this is what my alternative is. So that you know, let's say if you want to do a left-sided or a right-sided test, then you could see from here immediately, okay, I'm not doing the right test. I need to go make some adjustments. It also does a 95% confidence interval for you. It tells you what the mean of the data is, which we got a little bit earlier as well. It gives you your degrees of freedom, which matches what we expect. And it tells us that we actually have a very, very small p-value in this case. It also gives you your test statistic value. Now, you could have also gone and said, okay, I want to specify here that my, so here in this case, you can see we tested whether the mean is not equal to 0. Is that what we actually wanted to test? No. What did we want to test? We had a very different mean that we wanted to test. So just going to say here, firstly, I'm going to specify my alternative just because I can. And so you can see how to do it. So you do want to put it in inverted commas, and then we had to specify our mean. And our mean in this case is equal to 32.5. So that's the one that we're interested in. So if I run this, you can see I still have a small p-value, but now I'm actually doing a test to see if the mean is not or different from 32.5. So you can see my test statistic value is now 23.47. So not entering a value, or just assume that my null value is 0, which is not the case. And you can see it had quite the effect on my test statistic. P-value, not so much. So it's actually quite odd that it's giving me the same p-value as before. That's quite interesting. Maybe because the data looks very different from, so we're quite far into the tail ends. That could explain it. So we do have our 95% confidence interval. You could also have specified a different confidence level here if you wanted to work with 99 or 90. By default, it's always going to be 95. Any questions so far? Mpumelelo, I see your hand is raised.
Yes, I actually want to ask about our significance level, our alpha in this case. How does it differ from a one-sided? Because we're working with two-sided, will we have to have our alpha?
Yeah, so R will do most of that for us. So if you're doing a two-sided test, let's say, for instance, I put here, let's say we want to do a 90% confidence, or use a 90% confidence level. So I'm going to put this as 0.9. So if I run this, you can see here that it specifies that it's now a 90% confidence interval. So you don't actually need to do that splitting. Technically, what's happening is it's splitting the 10% alpha into the two tail ends. But it does everything in the background for you. You don't need to worry about that. So as long as you know alpha 0.1 means confidence level of 0.9, you just input that confidence level and it will do everything else in the background. But yeah, technically in the background, it does, if you were doing this test by hand, you would have taken that 0.1 and split it into the two tail ends for a two-sided test. If it's a one-sided test, all of alpha goes either in the upper tail or the lower tail. Does that make sense?
Yes, thank you very much.
Okay, perfect. Cool. So now we have this, these results. It's printed out and all of that, but I wanted to show you, you can also assign it to a object. So let's call this test 1. It's the first test we're doing. So I've created that, and you can see that what happens is R saves this as a list of 10 objects. So you can then access these things the same way as you would access things, elements before. So you can say test 1 and then $, and you can go and specifically choose the statistic. So you can just output your statistic, or you can say you want your parameter. Let's just do that again. You want just the parameter. So you can access these things. So for instance, let's say you're doing a simulation study and you're going to do tests repeatedly on each of these simulated samples. Then you may be bootstrapping or something, and you're doing a test each time, and you want to extract your p-value. So you want to use this function and you want to extract your p-values and save all your p-values into a vector. Then you can go and do it this way, and you just say, I want my p-value, and you can assign that p-value into a vector. So I see it here, it is giving me the actual p-value. Here it's giving you just a, I think that's probably a limit that they've set, and so they're not giving anything smaller than this value in this default output. But if you actually go access the p-value itself, you'll get a more exact answer. So you can see here all the different things you can access, what's in there, and all of that. So that's basically, you can see your standard error. You can see some things that weren't necessarily displayed in the default output. So all of this is available again. Any questions about that? Yeah, you can see you don't even need to know the actual formulas. Yes, Isaac. Isaac, did you want to ask something?
Give us someone. I think where we have the position $sign, the till. I think there's a function that we can use to detach that one, that we can only use the till underscore L. Like if you use that attach. So I was trying to find out, is there an advice that you can give to someone who fall on that instead of your approach? I don't know if my question is clear.
No, I'm not 100% sure what you mean.
Okay. Where we have can you please help in typing it?
Can I? I'm sorry, you're breaking up a little bit.
Yeah, I say, can you help in typing it? We can, where we have.
Yeah.
We can attach like the word attach.
Okay, attach. Yeah.
Yeah, then we'll put the data set position.
Is possum, yes.
Yeah. So you can click enter.
Okay.
So with this one, we can now access the various columns in that data set without using the dollars. And so I'm asking probably if there is an advice, or maybe, I will use a certain approach of which you said there is a problem that you have with the length. So I was also trying to find out if maybe there's also a problem with this approach, because I kind of always see you using this approach a lot, like using the position under $sign, then the columns if you want to access a column.
Yeah. I'm still not I'm still not 100% sure what you mean from this point onwards.
Okay, so from this point onwards, I think if you type till underscore L, I think we can now access the
Okay.
No, not the till that, like the till.
Yeah.
Till.
Can you maybe type that in the chat, and then I can just see what you mean? I'm not 100% sure what you're referring to. Okay. Tip. Okay. So that's
yes.
Yeah, so I see then that's also a nifty way of doing things, that you just work with the variable name then, instead of having to reference the data set and accessing it in this way. Cool.
So I was asking maybe if there is, because mostly I kind of use this approach a lot, so I don't know if there is also some hinges or with that one. That's the reason I wanted to know if there is an advice that you have for people who uses, just the attach, so that you can, instead of always accessing it with the data frame and then the column, if there is maybe, if my approach is, there is always a problem with that approach. So I just want to know if there is an advice for.
So basically, do we want to see if this would work if we used it in this manner? Let's see if we use tail underscore L. It does look like it's going to actually work because it recognized what I was doing. So I'm just typing the rest of this quickly. And then let's say mu is, I'm learning nifty tricks from you guys as well. Cool. Confidence level is 0.9. Let's run that. And then let's just see what the output is. There's 1A. And I'm just going to output my one as well. And then we can compare that. It does look like it gives us the exact same result. So that's another way of doing it then. Also learned something new today then. Let's just do that. I'm just going to copy this. So this is maybe an easier way if you don't want to keep referencing the data set, then this could be a nice way of doing it. Thanks for that one. Cool. So yeah, so that is basically the one sample t-test. You can see very straightforward in R. You don't have to do a lot of thinking. You just have to make sure that it makes sense for your data set. But that's the same for any data that you use. You need to make sure that what test you use actually fits with what you're trying to do. You're not using a test that you're not allowed to use. Yes.
Can you please rerun your code again?
Yeah.
The one which is not using the tail alone.
This one.
Yes.
Okay. And you just want to see the output.
Yes.
There we go.
All right. So it's still working. Yeah,
it's
but
still
I just wanted to check if if it executes, because there is the opposite of attach is detach. So I was just thinking of like situations in which you may fail to do something when you have attached your data set. But I can see that it still works. Then I'm now failing to understand now the reason of de-attaching.
Yeah, I think maybe it's just to clear memory. That could maybe save a little bit of memory if you don't have a bunch of things attached still, because I think it does go into your memory if you bring it forward. So that's maybe one reason. If I'm wrong, someone please let me know, right. But that would be my best guess.
Yeah, thanks so much.
Yeah, no problem. But yeah, R is actually quite forgiving as well. It's not a difficult language to learn. It does help you along the way quite a bit as well, and it gives you really good messages also when things go wrong. So easy to use in the end. So yeah, so that's pretty much, that was my bit for the first test. So the second test I wanted to look at today is the two sample t-test. So this is used to test theories when we're comparing two population means using sample data. So we want to make inference about these two population means, and again, when standard deviation is unknown. So there's a lot of information available that you can get about the assumptions. So I just listed a few of the common ones that I found. So small sample size, again, same as with the one sample test. If it's small samples, and again, it could be less than 30, it could be less than 50, depending on the source that you're using. Your data needs to be approximately normally distributed. For large samples, it's not a big train smash if it isn't, because the central limit theorem helps you out then. So then your sample, again, needs to be random. And now what's added here is the observations in your one sample need to be separate or independent from the other sample. So you do also get a two sample or a paired t-test, where you can, for instance, do a before and after observation that you're comparing with each other. And that is same function in R that we just used. It's just you're going to say you have paired observations. But otherwise, for the one that we're looking at today, we're doing the independent samples one. And then it is best if the samples have approximately equal variances. If they don't, there are actually t-tests available for that as well. And you would remember from the help file that we saw just now, it said there, or it gives you an option to indicate whether you have equal variances or not. So then your two sample t-test basically is a comparison of these two means. So for that, you, sorry, I'm just trying to find my mouse now. It has disappeared. Ah, there it is. You're looking at a difference, and you can specify that difference. Often, if you just want to compare two values, you're not looking for a specific difference that D0 will be 0. Otherwise, you could say that you want to check if the one is at least 5 bigger than the other one, then you have a specific difference that you're interested in. And again, your rejection criteria is based on the T distribution. This time I didn't specify what your degrees of freedom, how to calculate them, because that will depend on whether your variances are equal or unequal, and some other things. So we're not going to worry about that just now. So what I want to do is I want to look at possums again. And let's say we're interested in seeing if male possums are longer, they have a longer total length than female possums. So some more pictures of female and male possums and baby possums. They are very cute. So we can phrase this statistically in two ways. So you can write it as male minus female, the average male length minus the average female length. And we're not interested in a specific difference, so we're just going to work with a mean of 0 here. Or we can say female minus male. So it's just important when you do this to recognize that the direction of your test will differ. So for the males, if you say male minus female, if the males are longer, then that difference should be greater than 0 because you have a larger value minus a smaller value. Whereas if you had phrased it as you're going to take female minus male, then you need to say less than 0 because then obviously it's a smaller minus a larger value gives us something negative. So the direction of your test, you just need to be careful with on if you have two sample cases, specifically keeping in mind in what order you're going to enter your values. So if we go back to R, you'll see that in the file, I've already added a few things in here just to save us a little bit of time. Also had a lovely spelling error there. So we want to test whether female possums are shorter than male possums. So they have smaller total lengths. So what I've done already is I've said I'm going to subset my data and create two data sets. Now I noticed for the first time just now that there is a subset argument in here as well. I haven't used that. So maybe that's something for us all to go and try after today and see where we could subset automatically in that function. So I've just created the male and the female data sets. And we can see here there's 43 and 61. If we go back to our possum data set, summary, or let's actually use the table function, table of possum, and there we go. And we can see that we should have 43 females and 61 males, and that is what we end up with over here. So always doubt yourself, always double check everything you're doing. A computer only does what you tell it to do. So if you get the wrong results, it's your fault. So always double check. So then one of the assumptions is equal variances. So I haven't explained this test, but it's the variance test that you can find in R. So if you go check var test, it explains this test again. So it's an F test comparing two variables. Sorry, I just have my zoom in front of this. Let me just minimize this. Two variances of samples from normal populations. And there's all the information you need. So I've just applied this test and I said, let's look at the males, the total lengths, and the female total lengths. And we want to check if that ratio is equal to 1. So with the F test, what you do is you take the ratio of the two variances. And if they're the same, then that ratio should be close to 1. Or if they're very similar, it should be close to 1. The further apart they are, the further away from 1 that ratio will be. And then that, I was typing on another screen and apparently I typed here as well. So we can specify our alternative and specify our confidence level. And now I've made a mistake in here. Anyone, can anyone see the mistake? Yes?
Is it I think the confidence level normally should be from 90 about 1. I don't seem to understand it.
Perfect. Confidence level should not be that's my significance level. There's another mistake.
So I think that one should be the critical level. Can we specify the critical level there?
The critical level.
Yeah, the critical level, the alpha value to maybe 1.
So remember, the alpha is derived from this. So if your alpha plus your confidence level together should add up to 1. So we only specify the 1. We don't need to specify the other one. Now, someone said in the chat, maybe this should be one-sided. But remember what we're trying to test here. We're not doing our t-test. So the t-test will be a one-sided test. But at the moment, we're testing whether we have equal or unequal variances. So that's why I've made this two-sided. So I'm going to run this code because this is just a prelim just to see what we need to input into our t-test function. So I'm going to run this and let's see if R picks up the mistake. And you can see R does pick up the mistake. I've written 2 dash-sided, not 2 dot-sided. Yes, Floyd?
No, I was about to say that it was supposed to be 2 dot-sided.
Yep. So you can see what I mentioned earlier was that R is very forgiving and it's very helpful. If you get stuck on something and you've done the wrong thing, it might actually point out your mistake very clearly to you. So if you did this, then it will tell you, oh, no, these are your options. So stick with these things. We don't know what else to do here. So that is the test. And if we look at this test, we can see here, it's testing whether the true ratio of variances is different from 1. We have a very large p-value, which means that we don't reject the null. And the null in this test would have been that the variances are equal. So when I do my t-test now, I'm going to assume that I have equal variances because this test tells me we're on the right track. We have equal variances, or we should have equal variances roughly here. So now I can use my t.test function again. And I now need to enter things a little bit differently because now I have 2 data sets. So you can see here we have an X and a Y. So I'm going to enter, let's say the males first. So male total length. And then I'm going to use female total length. And then we need to look at the other argument. So alternative in this case is now definitely not going to be two-sided. Which side should it be? So should I say less or greater?
I think it's
less. Okay, let's put less, and then let's go back to this. So our first sample here is male and then female. So if we look at what we wrote here, if we say male minus female, it's actually greater.
Oh, it's greater. All right. Yeah.
So it's always a good idea to just write this down before you touch the computer, work the logic out, see what the direction is, and then you go, because it's very easy to make a mistake like that. So I'm very happy that it did happen. So we want greater in this case. Perfect. And then our mu in this case, what would our mu be? So again, we can go back. So this hypothesized value, if we look at this, what is the hypothesized value? Or the hypothesized difference? Sorry?
0.
Yeah, exactly, 0. So again, by writing it out beforehand, we know exactly what the answers are. So this would have been 0 by default. I'm just typing it anyway. And then paired, I'm going to say here. So now we have a few more things that we need to enter. So paired in this case is going to be false because I am working with 2 independent samples. So if you were doing a t-test with dependent samples, so paired t-test, then you would obviously go for true here. And then we can say here variances equal. And in this case, we've done our test. We're happy to say, yes, this is true. So if I run this, I get my test results, and we can see here, we get a very large p-value, and it's telling us basically we don't have evidence to say that the males are longer than the females or the females are shorter than the males. So that's pretty much it. So we could have also gone, let's say we didn't do this other test. You could have done this and said, let's for safety say this is false. We run this, you can see we're actually getting something very, very close to that result. There's not much difference in our results here. You can see though, our degrees of freedom are calculated quite differently. So there are some differences. There are some differences in your confidence intervals as well. But yeah, in this case, it doesn't make too much of a difference. So yeah. Any questions so far? Everyone happy still?
Hello, Chris.
Yes.
Like I would like to know. I'm so curious to know. It has been a while since I learned this distribution. Now, if you look at the number of males and the number of females, they are different. I think one is 65, one is 47 or so. That was kind of imagining how the system is able to do the calculations, because if we should map it 1:1, we'll be left with more males more than the females. So I was much curious to know.
So actually with this test, when it calculates your test statistic, what it does is you're calculating the average for all the males and the average for all the females, and then you're subtracting, so you're saying the average, so X bar for the males minus X bar for the females minus your hypothesized difference, which is 0 in this case, and then you divide by, and that what you divide by will depend on whether you have equal or unequal variances, but it's basically your standard error of the difference between the two sample means. So that's calculated differently depending on whether you do equal variances or unequal variances. The one formula is a nightmare, the other one is quite simple to understand. But yeah, the basic idea is just you average the one group and you average the other group. When you do a paired test, so when you have like before and after or matched like pairs of data, then you would take differences first and you average those differences. So that's where the big difference comes in with the paired test versus the not paired test, so the independent test. The one you first average and then subtract, and the other one you subtract and then you average.
I think I'm okay with that. I'm okay. Yeah, another one to at first where the confidence, you have the confidence level is you wrote 0.01, and you were if I heard you were saying that you can leave 0.1 there. Something I wish maybe you could throw light on that again for me.
Okay. Yeah, so your confidence level and your alpha. So if you calculate your significance level, or you take your significance level and you add your confidence level together, they give you 1. So I had typed my significance level there instead of my confidence level. So that's why that was a mistake. So we would not want to have 1% confidence in our results. So in this case, we could say we're 99% confident in our results. So that's a good confidence level to have. It's not a good idea to have a 1% confidence level, or be 1% confident in our answer.
Okay, so is it always that we have to use the confidence level instead of the alpha level?
Yes. So these tests all specify your confidence level, not your alpha level. And I think that's why I also probably typed it that way. I had actually made the other mistake on purpose. That one wasn't on purpose. So I'm glad you picked it up. But I think a lot of software, you type the significance level. So we're so used to using our significance level that sometimes you do it by accident. So it's just something to pay attention to, because I've just illustrated how easily it happens. Yeah.
Okay.
Any other questions?
And Simpumelalo's hand is up.
Okay.
Yes, thank you. I actually want to ask about the F test. So we have to perform, okay, there are just two questions quickly. The first question is, do we always have to perform the before we perform the two sample t-test? And then second, what happens if the variances are not equal?
Well, if the variances are not equal, then you do have the option in here to specify that your variances are not equal. So that's what I did in the second one. And then the test will automatically make the adjustments in the calculation. So it might use some other formulas. There's a few different approaches to use. The F test, it is probably a good idea to do it, but there are some pre-requirements as well for that one. So I didn't go into the assumptions for the F test, but I know the F test also really wants you to have your data from normal distribution. So I haven't actually checked this one, so let's maybe quickly do that. If we do a histogram of, let's say, I'm going to do everything together just to start off with. But let's do it for the possum total lengths and see if it at least looks semi-normal. Doesn't look that normal to me, to be honest. So yeah, not the prettiest one, but if you think about it, it's also not the large sample. So maybe that could have something to do with it. We could do a QQ plot as well and see if it looks normal enough to us. There could be other tests as well that you could do to check for equal variances. I know I read recently when I was busy preparing for the lecture as well, you don't necessarily have to do an F test. So I just did it now to show you what it looks like, but you'll find that there's some more like rule of thumbs that you can use. So if as long as the one variance isn't more than 4 times the other variance, then they find it acceptable to assume equal variances. So I can't remember, I think it's 4 times, I could be wrong. I remember reading it though, but yeah, it's not necessarily necessary to do the F test. There could be other ways of judging it as well.
Thank you very much.
Perfect. Okay. Any other questions before we move to the last test? Okay, no other questions. Perfect. Okay, so then let's go to the last bit. And now we are done with the possums. So we have someone requested that we do the chi-square test for independence today as well. I can't remember who put the request in, but I've added that in. So of course, this test also has quite a few variations. So you get a chi-square test for homogeneity, you get for independence, you can get chi-square test to test whether your data follows a specific distribution that you pre-specify. So there's a whole bunch of variations on this. I'm just going to look at specifically for independence. So it is basically used if you have numerical variables and you want to compare them or you want to check whether those variables are independent of each other, then you do that by looking at what would you expect it to look like, the frequencies in the different categories if the data was independent or the variables were independent. Versus what you're actually observing. So that's where this formula at the bottom comes from. It basically says in each of my categories, you can kind of imagine, let me actually draw a little table here. So you have your variables with the different levels. So that's your variable 1. Here you have variable 2. This is level 1. That's level 2 for that variable. And of course, you can have a lot more than just 2 levels per variable. But basically what you do is you have your observed values in each of these categories, and you also calculate then what would you expect to see in each of these categories. And then you go and look at the difference between what you're observing and what you expect to observe. You square that difference and you divide it by the expected frequency. So now logically, if you think about it, if the variables are independent, then what you observe and what you expect to be observed should be very close together, which means that this difference should be very close to 0. When you square it, it's still very close to 0. You divide it by something, it gets even closer to 0 because you're dividing it by something. So when you add all of these values for each of these cells, you should end up with a test statistic very close to 0 if your variables are independent. If your variables are not independent, then you can expect big differences between observed and expected values. And when you square that, that enlarges it. And yeah, you end up with a test statistic which is much larger than 0. So the chi-square distribution, we haven't really spoken about the chi-square distribution, but it's a skew distribution. It starts at 0. You can't have negative values on the chi-square distribution. It starts at 0. And when we do this test, what we're actually doing is always a right-sided test. So you have 0 over here. And if you have, if your data, your two variables are independent of each other, you expect your test statistic to lie here on the left-hand side. So a small test statistic indicates that you have that independence. Where if you have a large test statistic, it's because you don't have the independence. So that's kind of what we're looking for here. So our assumptions or our requirements in this case, I made it a little bit of both, is both variables are categorical, or you could have for your variables also that you've put them into categories. So let's say that you have, you'll see an example we have now is the amount of time that a person sleeps. Now that's technically not a categorical variable unless we go and put it into categories. So then we are treating it like a categorical variable. So then also our observations should be independent of each other. So in other words, we want a random sample. Our data should be frequencies, so not percentages. So these expected counts and the frequencies that we have here are frequencies. It's not transformed data, it's not percentages. Then also these expected frequencies, when we calculate them, should be at least 5 in each category. I did find something online where someone wrote at least 80% should be at least 5. In all the years I've taught this, we've always stuck with make everything at least 5. Otherwise, you need to start combining categories because if it gets too small, the test isn't valid anymore. And then the levels of the variables should be mutually exclusive. So in other words, you can't be in multiple cells. So if you're in this one, you can't also be in that one simultaneously. So you're either in the one or in the other, you can't be in both. And then how we phrase this test is our null is that we have independence. Our alternative is that the two variables are dependent. And then everything else is based on your chi-square distribution. And I've shown you how the test statistic works. So I see Mpumelelo, your hand is up at the moment. That's still from earlier, or do you have a question?
No, sorry, I don't have a question.
Okay, perfect. Okay. Any questions from anyone before we move to the example? No questions. Okay. So the example that I have is based on sleep deprivation, which I think we're all starting to suffer from already this time of year. So there's a sleep deprivation data set. It is again in the open intro package. So we did load that package earlier, so we don't need to load it again. And it is a survey conducted on the sleep habit of randomly sampled transport workers and a control sample of non-transportation workers. So we want to test to see whether there's a dependence between a person's profession and the amount of sleep that they get. So our null is always that we have independence. Our alternative is always that there's a dependence. So if we go over to R, first thing I want to do is actually look at the sleep deprivation data set just to get an idea of what's happening there. So we are just going to go view the sleep deprivation data set. And if we've done that, you can see here, there's a control group. There's less than 6, so the sleep is in categories. Maybe we can just do a summary of this. That's maybe easier. I like just always looking at the data quickly and then doing my summaries just to get a feel for what to expect. It's always so nice to see if there's missing values, if there's anything we need to worry about. So I'm going to do sleep deprivation. Let's see if what tells us there. So you can see there we have different categories: less than 6 hours, more than 6 hours, 6 to 8 hours. It doesn't matter in which order we put these. It's not going to make any difference to our calculations. Then we have bus, taxi, and limo drivers. We have a control group. We have pilots. We have train operators. We have truck drivers. So we can do this test now using all of our data, or we can go and subset and say, okay, I'm actually only interested in comparing certain groups. Doesn't matter. So we can do whatever we want in this. We can play with it. So now the next thing we need to do is we need to go and do our test. Any guesses on what the function is going to be called?
Crosstab.
Sorry?
I think it's crosstab.
Okay, so there's no function like that. So we want to do a chi-square test. So I'm gonna, so Isaac is saying chi-square test, and yes, there is a function like that. So if we go back down here, we can go and check the notation. It's so easy, you can just guess this stuff. So there's the chi-square test, and we can then go and see what notation is, or what the syntax is, what arguments are required. So there's an X, there's a Y that you can enter. Correct is true. I don't know what correct is. It's a logical indicating whether to apply continuity correction when computing the test statistic for 2x2 table. So good to know that that's there. There's something with P, where they explain all of these things. But it looks like we can actually get away with just 2 arguments in this case. So there's also, again, details if you want to read a little bit more. If you're not lazy like I am, then you will go and read that. There's some more information in here as well. And there's a source where you can go and see where this comes from. So there's references, always useful when you're doing your research and you're using a test. If you want to go make sure this is like the right test, that you're not missing assumptions, then you can find those references. And then there's some examples. So let's go and try this. So we have chi-square test, and I'm going to do sleep. I'm actually going to use that trick that we just learned. So attach, and let's do sleep deprivation so that I don't have to tap the whole thing every time. So there we go. And then we know the names, and there will be sleep and profession. So I'm going to put sleep. Let's see if it works. And profession. And let's run this. And there we have it. So it gives us the chi-square value. So this is our test statistic value. It gives us our degrees of freedom. It gives us our p-value. You'll notice it's not specifying a direction for me, because a chi-square test is always an upper tail test, for the reasons that I explained earlier. So there's no need to actually specify the direction. That's why we also don't have it in the arguments here. There's no point in doing a left-sided test, because what would that actually show us? So that is basically it. So then we can again just go and let's call this test 3. We can assign it in there, and you can go look at that list, and you can see what we have available here is, again, our statistic. You can extract your parameter, you can extract your p-value, you can extract the method that was used, what the data was called, the observed values, the expected values, the residuals are in here as well. So there's a few extra things here that I'm sure you can go and read about in the help. And yeah, that's basically how you would do a Pearson's chi-square test in R. Very straightforward. Any questions about that? And one other thing that I can add is I actually haven't looked for a data set specifically. I'll see if I can find one before Friday. If we do this test, maybe subsetting some of these, if we violate those assumptions that are needed for this test, R should give you a warning about that. So let's just maybe see if we do this data set. I don't think it will work out very well because it's quite a large data set, but I'll see if I can find us a smaller data set where we're going to run into those issues, and then I'll show you on Friday. Any questions or comments? Or any requests for Friday's class, anything specific that you guys would want me to show you on Friday? Can still adjust.
What can be our conclusion regarding the relationship between someone's profession and the amount of time they sleep? Can we conclude something meaningful?
Okay, so if we look at this, if we were making our decision at a 5% level of significance, you can see here our p-value is larger than 0.05. So at a 5% level of significance, we don't have evidence to say that there's a dependence between those two variables. At a 10% level, you would reject the null hypothesis in favor of the alternative, which says there's a dependence. So for this one, it's not very strong evidence, in my opinion, of a dependence, because you can only make that conclusion that there's a dependence at a 10% level. You can't even do it at a 5% level. So the smaller your p-value is, that's quite a useful thing with p-values. The smaller it is, the stronger your evidence is in favor of your alternative. If you have a large p-value, you don't have strong evidence in favor of the alternative. So if you've chosen your significance level, which is basically the level of risk that you're willing to take on to make a type 1 error, which is rejecting the null when you actually shouldn't have. So the smaller that alpha is, typically we work with 1%, with 5%, with 10%. So if you take at a 1% level of significance and you can reject the null, then you have pretty strong evidence supporting the alternative.
And what can you comment about the chi-squared value in this regard? Because 14.49, which is, I think, larger than 0, not very close to 0.
No, it's not very close to 0, but we have to keep in mind also that depending on how many of these cells we have that we are doing this calculation for, it is always going to increase. So because for each of them, we are going to add a value. So I did say earlier that the closer it is to 0, the better. But what we consider close to 0 will depend also on our distribution. So the degrees of freedom will determine how spread out the data is as well. So in this case, it's telling us that this is actually still relatively close to close enough to 0 that we're happy with this. It's not that far away from 0, the 14.49. So typically it's easier to make a decision based on a p-value than it is to make a decision based on this value, because to actually objectively look at this chi-square value, our test statistic value, we have to go find a critical value from the chi-square distribution with 8 degrees of freedom. So this value will vary. Well, how we interpret it will vary based on what our degrees of freedom would be as well. Does that make sense?
Yes, it does make sense.
Okay, awesome. Yeah, so typically people like to go to the p-value because it's already factored everything in. It's just a simple thing that we look at then. What goes into the calculation of the p-value is a different story. It's not that difficult if you know what to do, but there are a few small tricks sometimes to keep in mind. So it's nice that the software does it for us. So I see there's some comments in here in the chat. So statistical modeling, any specific modeling that you have in mind, Floyd? There's quite a lot that can be done. So I'm definitely planning on doing just some linear regression on Friday, just to show you what you can do in R with that. I can maybe show you, I mentioned earlier the QQ plots. If you want, I can show you some QQ plots on Friday as well. Kind of still falls in descriptives, but I can do that if you want. So Floyd, if you can let me know what kind of modeling you had in mind, then I can see what I can do.
Okay, the time is also, I think,
okay,
very fast now. So I think you will have an opportunity to finish and
perfect
by Friday. So
yeah. Perfect. Okay, so yeah, so regression seems like they're fine with it. If there's any other requests, just send it to me on Slack. Obviously, the sooner the better, and then yeah, we can have a chat on Slack, and then I'll include what you guys want to still see. Okay.
Okay, Christine, thank you very much for a very interesting lecture. I remember many years ago I did mathematical statistics, but some of the things are becoming clearer now. Yes, I'm
glad.
I trust students are learning something, revising some topics that were, they attended many years ago. So to be, of course, useful to them. Thank you very much. And thank you, students, for joining. And remember, tomorrow there's another session in the morning. Thank you very much. Bye-bye.
Thank you so much. Bye.